Okay, everyone. In this video, we are going to really try to put together these concepts of these bulk properties, these big energy properties like internal energy, pressure, entropy, Helmholtz free energy, Gibbs free energy, etc., and try to link that back to the molecular properties that we were talking about with the partition function on statistical mechanics. So these properties are things like pressure and microstates and temperature and volume. And really, at this point, it's time we finally know enough that we can kind of start to put these together. Now, I'm going to show you some relationships today, and I'm going to ask you to trust me. If you really want to sit down and try to figure out how to derive from the partition function to these equations that I'm showing, it can be done. That's generally covered in an advanced statistical mechanics course. So we're going to just make sure that you have the concepts, and we're not going to worry about too much how to get from this partition function to these properties. Okay, so let's review. The Boltzmann canonical probability distribution. Remember that we have basically the microstates, the number of microstates, times this e raised to this energy term, divided by the summation over all possible microstates and energies. And that is the probability of finding something at a particular energy. Now, we often get rid of this summation and we write this out as Q of t. And it turns out that this Q of t, what we have been using as sort of a normalization factor, it makes sure that our probabilities run between 0 and 1 or between 0 and 100%. It's the total of our system to get us into this fraction idea. Well, it turns out that this Q of t that we've been using just to turn stuff into a fraction actually has a lot of meaning and a lot of usefulness when we start trying to connect these microscopic properties to these macroscopic properties. From Q of t, it turns out that we can get to all properties of a system at thermodynamic equilibrium. And this includes the energy, the entropy, the enthalpy, the Helmholtz energy, Gibbs free energy, the chemical potential, this thing that we'll talk about eventually, pressure, etc., etc., etc. It turns out that starting with this Q of t, we can get pretty much anywhere that we want to be able to describe the thermodynamics and the energies and the properties of the system. So what does this look like? Well, it's some complicated derivation because ultimately we have to be able to figure out the math of this summation. And the math of the summation is challenging. And so while we have done a fair amount of math this semester, we're not going to go there. Instead, you're going to trust me in that these derivations do work. We can start with Q of t and go to pressure. We have started with Q of t and gotten to entropy. We can go to the Helmholtz energy. We can go to the internal energy, and we can go to this chemical potential. All of these all of these terms, pressure, entropy, Helmholtz, energy, chemical potential, these are all macroscopic properties. And we can see that every one of them has a Q in that final answer. And so that means that starting with that partition function, if we can do the math, we can come out with every macroscopic property. And so that leads us to a really key thing about thermodynamics. Absolutely all thermodynamic parameters depend upon molecular properties. And these molecular properties are represented and modeled and explained using the partition function. And this is a really key thing to remember. So even whenever we start thinking more macroscopically of final minus initial and these changes in terms of reactions, these things all depend upon the molecules, the vibrational, the rotational, the electronic energies of these molecules. We cannot just think of a reaction as generic species running into each other, because each of these species in the reactions, they have their own molecular properties, and these molecular properties are governing the energies and the macroscopic observables and the things that we can measure about the system. Okay, so where are we going? From here, we are going to start working to get into explaining reactions. And before we really get to reactions, we're going to start with something basic. What happens if we just change things like pressure, volume, and temperature? And how does this relate to our work and our heat? And then we're going to expand that understanding of these cycles and these processes into, now let's add chemicals with chemical properties. And so from here, we're really going to get into what are known as heat engines and cycles and more sort of engineering. And once we have the engineering down, then we're gonna stick in the chemistry into that.